I'm going to divide my remarks into 4 parts. The first deals with the parties involved, the second with X, beta, and gamma rays, the third with Moseley's law, and the fourth with a puzzle that I wish to leave you with, a research puzzle. As you'll see, I place some emphasis on errors and poor guesses, not to be wise after the fact, or far less to criticize people who created something bold and important, but in order to point out that they were groping in the twilight. We do them an injustice to insinuate that their course was clear, or for that matter, that they were all sailing in the same direction. So I begin with the players. Moseley was 25 and Bohr 27 when, during the spring and summer of 1912, they were research students together here in Rutherford's physics laboratory. Although Rutherford already had a knighthood and a Nobel Prize, he was only a dozen years older than Bohr, who was already, as I intimated in my intervention a moment ago, who was already a man of distinction, at least in Copenhagen, where he had taken his doctor's degree with spectacular success and had won a gold medal from the Royal Danish Academy of Sciences for theoretical and experimental investigation of water jets. That didn't cut any ice in Manchester. Bohr was not only a foreigner and a tyro in the laboratory's main, if not its only, research subject, radioactivity, but he had come to Manchester without a reputation after 6 disappointing postdoctoral months in Cambridge. In marked contrast, Moseley was a veteran student of radioactivity, known throughout the laboratory as a skillful and indefatigable experimenter. Bohr could not help but notice him, as Moseley then was breaking a lot of glass apparatus trying to coax radium to charge itself up to 300,000 electron volts, 300,000 volts. As Niels has discovered, Bohr and Moseley boarded close to one another, at least for a time, and so would have had chances to meet in the street as well as in the laboratory. Nonetheless, they probably had no significant contact or conversation even during the months of 1912 when they were together in Manchester. At the time, they didn't have a common research interest. Neither mentions the other, as you now know, in their extensive correspondence with third parties, at least that I have seen. And in any case, they were not well matched temperamentally. Moseley regarded foreigners from the heights of Eton and Oxford and had the stereotypical prejudices of people so nourished. He did not make friends easily even among them. He had only contempt for the students he had to teach and criticized Rutherford, who had a breezy down-under manner, for acting like a stage colonial. Moseley's general conservatism, which included respect for and probably belief in the teachings of the Church of England, would not have opened common ground with the freer-thinking Bohr, who had then recently, as you know, renounced his membership in the Danish state church and inscribed himself as an agnostic in the Register of Hume Hall. I owe this precious tidbit also to Niels. Without seeing this entry, but with his customary omniscience, Moseley had informed his sister that all agnostics are prone to frequent mental worry. In fact, Bohr was not an agnostic, but an atheist. He had reached this steady state by a quantum jump from a strong adolescent religiosity on realizing that, as he put it, the tenets of the Lutheran Church regarding salvation were nonsense. To ease what mental worry they had, both Bohr and Moseley cultivated wide interest outside science. That did not give them much in common either. Moseley loved natural history, his father's academic field, and developed into a knowledgeable and passionate gardener. Bohr, too, delighted in the out of doors, but as a theater in which he could walk and talk and think, he left flowers to the care of the God in whom he did not believe. His passion was everything intellectual, especially philosophical questions to which his father, whose field was physiology, had introduced him. Of course, there were countervailing factors that might have drawn them together. Each was the son of a university professor who died young, and each had a devoted and supportive nuclear family. A sister and mother in Moseley's case, a brother, mother, and fiancé in Bohr's. I have some pictures of these people. There is Moseley's mother, who was long widowed by this time. And here is Bohr with his circle. He's less goofy in his engagement, goofy looking in his engagement picture than in the photo with his mother, which was taken a few years earlier. So together with Charles Galton Darwin, who, like Moseley, was the grandson as well as the son of a scientist, together with Darwin and George Hevesy, a descendant of Austrian barons on both sides of his family, Moseley and Bohr constituted the aristocracy of a laboratory led by the son of a colonial flax farmer. There is the cosmopolitan Hevesy. Nevertheless, as Bohr recalled in interviews conducted 50 years later, those interviews of 1962 that have been mentioned, no one at Manchester paid any attention to him at first except the cosmopolitan Hevesy and the colonial Rutherford. The sting stayed with him for half a century. A social and inquisitive man himself, he found the English, you'll pardon me, I'm just quoting the sources, xenophobic and uncurious, polite and so on, but they wouldn't be interested in seeing anybody it takes half a year to get to know an Englishman. Bohr could not afford the time. So he stopped going to the laboratory after he had learned as much as he thought he needed to know. He then worked alone in his rooms at Hume Hall. You've seen this picture before. I just wanted to call attention to it to show that the amount of contamination in the laboratory would have discouraged Bohr, I think, if nothing else. Neither Bohr nor Moseley was engaged in work of any importance during the first 3 months of their coexistence in Manchester. Then Bohr, the journeyman, descended from Hume Hall to show the apprentices of the laboratory what he could do. Darwin had supplied the opportunity by writing a paper on the absorption of alpha particles. Bohr diagnosed the calculations as nonsense, drew up a paper correcting Darwin's treatment of the problem. And the letter that Finn showed you, in which he tells Margareta that he's about to have some interaction with Darwin, was owing to his correction of Darwin's physics. Darwin amiably agreed with his errors, and the two eventually became friends, I suppose, after the statutory half year. More importantly, for the rest of humankind, Darwin's intervention brought Bohr to consider Rutherford's nuclear model, which Darwin had taken as the basis of his calculation. Bohr discovered that the model suffered from very severe disabilities. Disabilities so great that it had to contain more truth about the microworld than Thomson's so-called plum pudding model. This is because the plum pudding had been cooked up to obey the recipes of ordinary physics, which, as Bohr had persuaded himself in his thesis, could not account for the existence of stable atoms. So it's just because it's so bad that it looked good to Bohr. By the time he left Manchester in late July for his wedding on the 1st of August, Bohr had set down a preliminary foundation for what would become, some 8 months later, the quantum atom. He had not finished his paper against the Darwinian theory, however, before he left, and he had to return in August to complete it. He brought his new wife, Margareta, who thus began her honeymoon in the romance of a physics laboratory. From her martyrdom, Here she is with Hevesy and Bohr. From her martyrdom, we know that by August 1912, Bohr and Moseley had made some social contact. For in the only surviving exchange of correspondence between them, dating from over a year later, Moseley asked to be remembered to Mrs. Bohr. 2 months after this fleeting meeting, Moseley learned that Max von Laue and his associates in Munich had obtained some sort of diffraction pattern by passing X-rays through crystals. Here is the experimental result, A, and in B, Laue's reconstruction of it from his theory of diffraction. Manchester then did not do X-rays, but the laboratory had an endless supply of gamma rays, and Moseley tried to reproduce Laue's experiment using them. He failed, of course, and his failure induced him to learn the relevant experimental technique, which he did from William Henry Bragg at Leeds, and also to team up with Darwin to try to interpret the results that Laue had published. They discovered, as Moseley put it with characteristic cheek, that the Germans who did the work entirely failed to understand what it meant and gave an explanation that we saw was obviously wrong. After much hard work, Darwin and I found out the real meaning. They had hit on the same explanation given by William Lawrence Bragg a few days before they tumbled to it. That was a pity, as the explanation was worth a share in a Nobel Prize. Laue got one too, without sharing, although in Moseley's opinion, he did not understand his experiments. With Darwin's help, Moseley perfected his apparatus and identified sharp, characteristic X-ray lines against the general background radiation. Their paper describing their results appeared in the July issue of 1913 of the Philosophical Magazine, exactly the same issue in which Bohr's first paper of his trilogy on the quantum atom appeared. I come to my second part on X, gamma, and beta rays. Now, Rutherford had tried very hard to prevent Darwin and Moseley from taking up X-rays. He did not welcome experimental investigations in his laboratory in fields he did not control. He had acquiesced in the X-ray work only when Bragg generously agreed to advise on apparatus and technique. Nor, as evidenced by his earlier efforts to restrain Bohr from bounding ahead with the nuclear atom, did he like extrapolations that outran experimental evidence. He had dragged his feet when Bohr told him that the best evidence for the nuclear model was the principle of atomic number and the concept of isotopes, both of which Bohr considered absolutely obvious inferences from the structure of the nuclear atom, its distinction between nuclear and electronic processes. Rutherford thought he had good reason for doubting these inferences, that is, atomic number and isotopes. And he was able to strengthen his doubts about Bohr's concept of isotopes by using Moseley's technique of X-ray spectroscopy. The question at issue was to account for the beta ray spectrum of radio elements that also give off gamma rays. It appeared that from one and the same atom, you could get beta rays of 10 or 20 different fixed velocities. But in an important piece of work, Moseley had demonstrated that almost certainly in beta decay, only one particle comes off per disintegration. So how then did the vast beta velocity spectrum arise? Well, Rutherford supposed that both the electronic structure and the nucleus were the origins, could be the origins of radioactivity, the nucleus giving forth alpha particles and the electronic structure, presumably close to the nucleus, sending out an occasional electron, that is, a beta particle. Now, if the beta particle gave up energy in fixed amounts going through the electronic structure and so produced gamma rays, then if the gamma ray energy was absolutely fixed, then the emergent electron could only have the initial beta energy minus fixed amounts depending upon how many gamma rays it had produced. I didn't say that very well, but here you can see what the story is. So following this notion, Rutherford accounted for some 10 lines in the beta spectrum of radium-C, assuming only 2 sorts of gammas, and as necessary, the production of several of each kind as the beta particles sped through the atom. The calculations required the relativistic energies of the beta particles. Rutherford chose the wrong relativistic expression when trying to go from the observed velocities in the spectrum to their energies. Moseley pointed out the mistake to him and reported Rutherford's reaction to his sister Marjorie. He philosophically acknowledged his error and declared that even if the calculations no longer fit the theory, which was made to suit them, he is sure the theory is right all the same. So Rutherford redid the calculations with the correct formula and found agreement again with his theory, although with new values for the energies of the gamma rays. Indeed, the problem was more numerological than physical. Well, Rutherford was finishing up the first version of his theory of beta rays at just the time that Bohr revealed to him the concepts of atomic number and isotopy and the displacement laws, which required the beta particle to come from the nucleus. And since his revelations destroyed Rutherford's theory, Rutherford did not exhibit the enthusiasm for Bohr's new notion of the atom that Bohr had expected him to do. He stuck to his beta-gamma theory, partly because it had some quantitative backing, more, I think, because it had the common sense support of deriving the alpha particle from the nucleus and the negative beta particle from the electronic structure, and perhaps most importantly, it remained within Rutherford's comfort range, almost within his personal domain. He had distinguished and named alpha and beta particles and studied their characteristic progress through matter. Questions about their origin and nature had occupied him for over a decade. He thought that he had answered them with the theory he was completing just when Bohr's extrapolations threatened to destroy it. Rutherford continued to elaborate his account of beta and gamma rays with finer and finer experiments and stranger pictures until World War I put a temporary close to the subject. The refinements employed the failed experiments on gamma diffraction with which Moseley began his interaction with X-rays, and furthermore, 2 pieces of information that had been obtained by students of Thomson well before Lauer's discovery. One of these students, Charles Barkla, had found, as you all know, that metals struck by X-rays could give out 2 different sorts of characteristic radiations, one of which he labeled K and the other L, in order to leave alphabetical space for rays harder than K and softer than L. Now, this labeling proved prescient because Rutherford found that when he came to assimilate the gamma rays given off in his beta-gamma theory with characteristic X radiation, then he required sometimes characteristic radiation harder than K radiation. He called it H radiation. Barkla later thought that he had evidence of a super-hard characteristic ray also. He called it J radiation. Neither H nor J, as you well know, exist. There's no place for them in Bohr's atom. On the lower side of the alphabet, however, spectroscopists inspired by Moseley soon found M's softer than L's. In the last elaborate version of Rutherford's theory, which dates from 1914, a primary beta particle originating from or near the nucleus stimulated K and L rays from the electronic structure, and also, as necessary, his hypothetical X-rays. H rays. So there's the second version. Well, Enough said about that. In sum, Rutherford's preoccupation with the problem of the production of beta and gamma rays colored his view of Bohr's atom. He allowed for ancestor beta particles outside the nucleus, and he spoke of the vibrations of the electronic structure and the wave trains of the multiple gamma rays. Bohr's quantum jumps have no place for vibrations and wave trains. Although Rutherford calculated with Planck's H after modifying Moseley's apparatus to make possible the measurements of the frequency of gamma rays, his physical picture of atomic processes remained classical. I mentioned two important pieces of work from Thomson's laboratory, which came before Rutherford and his group in 1912, 1913. This was the experiments by Richard Whittington, his discovery of an empirical relation between the minimum speed a cathode ray requires to excite K radiation and the atomic weight of the metal so excited. Bohr had included this relation among the important experimental supports for the nuclear atom in the document he prepared for Rutherford in July of 1912. And this argument of his, which was published in the second part of his trilogy in September of 1913, was very simple. There is Whittington's law, giving the relation between the minimum velocity and the atomic weight, and here is Bohr's interpretation of Whittington's law, published in September of 1913. So, you see that had Rutherford reasoned as Bohr did, Whittington could have saved himself the trouble, and the result comes directly from the theory. I come to Moseley's law. The invention of X-ray spectroscopy made possible a neat test of quantum theory and the nuclear atom. Actually, I'd better show you. Yes, this is the figure we should have, because from Whittington's rule, you know that eventually, V being constant times what's the story there? You see? It's V. Oh, that V, I apologize to you for the font. That's supposed to be a nu. And so the argument is that since the velocity is proportional to A according to Whittington's law, that the square of the A is proportional to the energy. And if you believe in something like Planck's famous relationship, then you might want to associate a nu with the energy. And since A is proportional to Z on the nuclear atom, the weight's proportional to the charge on the nucleus, you should expect that nu sub K should be proportional to Z squared. Is that clear, or should I try that again? Anyway, you know from Whittington that the energy should go as A squared. You know from Thomson and from various other measurements that the atomic weight should be proportional to the what we now call the atomic number. Therefore, the energy should be proportional to the square of the atomic number, and therefore the frequency of the K lines, if they're associated with the innermost with the ejection of an electron from the innermost ring, should give you something proportional to Z squared. Okay, that's exactly what.
It's not proportional to the atomic weight.
Beg pardon?
Atomic number is not proportional.
It is close enough.
Well, the range of.
Yeah, but this I'm glad you say that. I mean, this is important. This is the standard way in which they were working at the time. Thomson's great progress in the theory of atomic structure was always couched as a connection between the number of electrons in an atom and the atomic weight. And when you go from Thomson's atom to Rutherford's atom, and the number of electrons in a neutral atom is equal to the charge on the nucleus, the same relationship was put forward. N is proportional to A. And in fact, by the time these experiments started, Rutherford's experiments on alpha rays, there was down pretty much to Z proportional to A over 2, which is not too terrible. And it's obviously true of helium, of alpha particles, and not too far off for platinum and so on. Okay, where did I get to? This is the way one could reason about what should come out of an investigation of the K frequency. Now, 3 months after Bohr was in Manchester in April, so then when in July, he came to discuss the second of his papers of his trilogy with Rutherford. I give you this chronology because, as you see just a moment ago, I got mixed up myself. Bohr was in Manchester in all these times in 1912 and 1913. Moseley was in town on these dates, and so overlap was possible, but not always. Now, Bohr was quite enthusiastic about this relationship between the frequency of the K lines that I showed you and Z squared. But he knew that the connection was not quite so simple as this one I have just sketched, because if there are more than one electron in the innermost ring, there will be a screening effect of one on the others, and or all the others on the one in question. And therefore, rather than Z, you should have Z minus some number which expresses the screening of the electrons within the ring. And this, therefore, would have been the formula which Bohr, in his visit of and discussion with Moseley in September of 1913, would have suggested as the outcome of Moseley's proposed investigation of the K rays, which is, of course, exactly what Moseley found. As he wrote to Bohr, giving the first fruits of the K lines, of his K investigation, the results are exceedingly simple and largely what you would expect. This was in November of 1913. The frequencies, for there turned out to be at least 2 K lines, came out to be proportional to Z minus 1 squared. And the constant in front of the R in the case of the softer of the K lines, K alpha, turned out to be 3/4. And so one could hardly resist likening it to the Balmer series, the Balmer formula, and to think of a Balmer-like transition as causing the K alpha lines. But to proceed, it was necessary to discover why sigma sub n was equal to 1. Well, Bohr made a lot of calculations of sigma sub n as a function of the number of electrons in the ring. And unfortunately, it turns out that there is not a bad fit at 0.96. If n is equal to 4, sigma is equal to 0.96, and therefore close enough to 1 to justify their, Bohr and Moseley's, belief that they dealt with a 4 ring in the closest to the nucleus. Moseley suggested that somehow in the collision that the electrons with cathode rays had produced the frequency, the K frequency, enough energy was found to raise the entire ring of 4, which then would fall back into its normal position, giving rise to, I suppose, 4 quanta K alpha, or maybe 1 quanta K alpha. Moseley acknowledged the improbability that there might be 4 simultaneous hits by cathode rays on the innermost ring to promote its electrons to the second quantum state. And to meet this emergency, he flirted with a heresy. He said to Bohr, in the only exchange of letters between them that is extant, "Is it possible that really no inner ring exists and that it is one electron vibrating by itself?" Then the factor z minus 1 would become z, and 2 elements somewhere, Moseley suggested the pair argon-potassium, where the chemical sequence reverses that of atomic weights, that they should have the same z. So 2 elements with the same atomic number. Then the impacting cathode ray would cause a single innermost electron to vibrate by itself, as Moseley put it, and everything would be clear. Bohr replied that the simultaneous excitement of 4 electrons was energetically impossible and suggested that K alpha originated in the filling of a hole in the innermost ring created by collision with the cathode rays. He did not comment on the impertinence of the concept of vibration in a quantum transition. It's interesting to have a look at what Bohr proposed as the solution to the z minus 1 question. The idea is he had convinced himself that there should be 8 electrons in the innermost ring. Cathode ray comes in, knocks out 1, there's 7. And then you can recalculate and find out how much energy is produced when the 7 ring again becomes 8. And you get this horrible expression at the bottom of the page, which if you cannot read, I have transcribed. And you would look then for an expression, some value of n that made the curly brackets expression, the curly brackets equal to 1. Turns out there is no such number. And so Bohr wrote to Moseley saying that he had stopped thinking about atoms for a time. It's interesting that about this time the Swedes began to enter into exact spectroscopy, and one of the group that formed around Sigbon in Lund, a man named Ivar Malmer, followed up Moseley's K alpha and beta measurements, and he too decided that the doctrine of atomic number was not necessarily to be accepted without doubt. He had found that he got a better fit for the K lines for antimony if he made it element 52 rather than 51 as Moseley's measurements of the L spectrum and the chemical evidence required. Accordingly, says Malmer, it seems to me that such an anomaly is possible and an element has not the same number in all spectral series. So once again, the experimenters are willing to give up the notion of atomic number. Rutherford was not secure about it. Moseley wavered, and now Malmer. Bohr never doubted it for a moment. Moseley's last research centered on the L series of the heavier elements. In what was to be his final published paper, he gave measurements of L alpha for 24 elements, including 7 rare earths. He was able to add 3 more rare earths at the heavy end of the sequence after examining samples brought to him by Georges Urbain, who had extracted them by laborious fractional crystallization. What Urbain called the loi de Moseley, essentially the principle of atomic number, unmasked the preparations that Urbain has supposed to be the heaviest earth as a mixture of lighter ones. Here are Moseley's notes on the samples that Urbain brought him to Oxford from Paris. It appeared that nowhere could be found an item called celtium, which Urbain had thought was the heaviest of the rare earths in his own private discovery. Here is the machine with which Moseley was able to test in 5 minutes what Urbain had taken a decade and a half to prepare. But all efforts to jam celtium into the sequence failed, and here you see Moseley's jottings on the business. You see circled 61 CT as one possibility, and down at the bottom, after lutetium, another possibility for putting in celtium. So you know, celtium doesn't exist. 61 doesn't exist naturally, and 72 isn't a rare earth. So here are the last measurements of Moseley on the L samples, and I want to call your attention to the last column on the right, which gives the wavelengths of the last 4 of the rare earths. Keep those numbers fully in mind, because they are the basis of the puzzle which I now put up to you and with which I will conclude. Moseley presented these results, in which he gave these numbers over on the right, to the British Association for the Advancement of Science at its meeting in Australia in 1914. He did not have time to write them up to his satisfaction before rushing back to England to enlist in the army. As he devoted the little leisure he had left, his training left him to his mother in his garden. But just before shipping out for the Dardanelles, he sent his mother the notebook in which he had recorded the details of the experiments he had recently made and his thoughts for further research. He admonished her to keep it safely. "I am sending you by registered letter my notebook, X-ray spectra of rare earths," he wrote. "I value it very highly." In accordance with Moseley's will, which bequeathed his papers and his property to the Royal Society of London, his mother gave the notebook together with his other writings to Rutherford as the Society's representative. According to her and Moseley's sister Marjorie, Rutherford promised to look into the notebook and determine whether there was anything in it worth publishing. Since he was fully taken up with war work, he passed on the task, I think, to an associate at Manchester, who was none other than Niels Bohr, who had come back to teach during the war in replacement for Darwin. It may be that Rutherford asked Bohr to check things out. That would account for a stray sheet in Bohr's hand listing Moseley's values for lambda sub alpha, the wavelengths for lambda sub alpha, the published ones, called Moseley 1, and the unpublished ones, which I'm sure you recall from your memorization of the previous slide, are exactly the numbers in the unpublished version, in the unpublished paper written after his experience with Urbain. The sheet also lists comparable measurements by Sigbahn, made in 1915 and 16. And Sigbahn, as no doubt you know, would receive the Nobel Prize in 1925 for his exact spectroscopy, another Nobel Prize missed by Moseley. Judging Sigbahn's measurements to be superior, Bohr or Rutherford evidently saw no point in publishing Moseley's. The notebook has been lost, or rather has not been found, in the papers of Bohr or Rutherford or in the archives of the Royal Society. That's a misfortune, as very probably it contained more of interest than the obsolescent measurements. Moseley easily could have published these measurements in a note to Nature. Since he did not, and since he valued the notebook so highly, it seems likely that it contained ideas not yet ripe about the relevance of his results to general questions of atomic structure. Certainly, he had discarded Bohr's original proposal that in the ground state of an atom, every electron has but one quantum of angular momentum. As early as February of 1914, he had deduced that the second ring had to have two quanta, and that, as he then wrote to Darwin, this is the key to the atom structure, and this little diagram I take from his letter to Darwin of that time. He invited Darwin to try to work out the properties of such a model and gave the misleading clue that the second ring has about 18 electrons in it. Another direction his thoughts might have taken was the identification of element 72. Perhaps the specimen of zirconium he examined contained enough hafnium, as 72, to make its detection possible if he had thought to look for it there. The stray sheet in Bohr's hand presents two intriguing details. The arithmetic in the box gives the values for the square root of 1 over lambda and shows that their differences are constant. This was just a check that Moseley's last L-alpha results agreed with his published formula. The carefully clipped corner of the manuscript is more suggestive. It could have contained a figure of the type that Moseley had sent Darwin. This figure may be taken out for purposes of publication or to draw up some sort of illustration for a lecture. The notebook may have contained something equally intriguing. Among Rutherford's papers are several pieces of stationery covered with calculations in Moseley's hand. The stationery came from the ship on which Moseley sailed home from Australia. Here are some of his jottings. The calculations have to do with Planck's radiation theory. Although they would not have made Moseley's reputation if published, they are evidence of an ability, or at least an interest, in working theoretically that does not emerge from his other writings. The manuscript sheet in Bohr's hand referring to Moseley's unpublished measurements is now in the Oxford Museum for the History of Science. It was found among the papers of the Oxford chemist Neville Sidgwick, who saw much of Moseley during the BA meeting in Australia, applauded his contributions to its joint sessions on atoms and molecules, and helped to popularize his experiments and the Bohr theory of the periodic table. Perhaps Sidgwick had the documents from Rutherford, with whom he struck up a lasting friendship during the long voyage to Australia. But he did not have Moseley's notebook. Had Moseley survived the war, he, rather than F.A. Lindemann, would almost certainly have been elected professor of physics at Oxford and thus become Sidgwick's colleague. And with equal certainty, Moseley would have had the Nobel Prize in Physics. Indeed, he got it, virtually, in the prize awarded to Barkla in 1918 for the discovery of the characteristic Röntgen radiation of the elements. Only one person ever nominated Barkla, and Barkla was nominated only once. The nominator was Rutherford, who thus circumvented the rules of the Nobel Foundation against nominating the dead and gained Moseley the Nobel Prize in absentia. That did not atone, however, for losing Moseley's notebook. I thank you for your patience and apologize for the beta gamma sword.